Hello, we are going to finish our Chapter 8 notes with two things. The first is using T procedures wisely, and the second is one last example problem. So the first thing to note is that we call something robust. A procedure is known to be robust if the calculated probabilities are still accurate even when a condition for inference is not met. And inference method is known to be robust when calculations are accurate even if a condition is not met. And specifically, T procedures are robust against non-normality. So what that means for us is that even if the normal condition isn't perfectly met, we can probably still use our T interval. We are going to write an edited normal condition for T. Now this is only for T. So this is only when we're doing mean things, well, things with means. So not for proportions, but let's start by our normal. Our normal condition says if n is greater than or equal to 30, our sample size is big enough, the central limit theorem holds, and we are totally okay no matter how skewed the population is. We can use P procedures no matter the skew. So we're happy in that scenario. But that might not always be the case. What if our sample size is a little smaller? What if our sample size is between 15 and 30? If this is true, we can still use our T procedures if we have some skew. So it is okay to use T with some skew, but no outliers. Now, when I'm talking about skew, we're talking about our sample distribution. And so for this condition, you are going to need, and I'll point to this here because we'll need it, you will need to plot your data. And last but not least, what if our sample size is super small? What if it's less than 15? Well, guess what? T procedures are so strong that we can still use T even in this scenario, as long as our sample distribution is approximately normal. We can still use T if our sample distribution has very little skew, I will say. Again, there can be no outliers, and the only way I would know this is if I were to plot my data. How do we plot our data? Well, we put our data into list 1, and then I think the easiest way is to make a histogram. Otherwise, they would give you the set of data if they needed you to check it. So let's look at one last example. A principal at a large school claims that students spend at least 10 hours per week doing homework on average. To investigate this claim, an AP statistics class randomly selects 250 students from their school and asks them how long they spent doing homework during the last week. The sample mean was 10.2, sample standard deviation was 4.2. Construct and interpret a 95% confidence interval for the mean amount of time doing homework. So I'm going to start by saying, hey, I know n is equal to 250, our sample size. I see that the sample mean, x bar, is 10.2, and the sample standard deviation, s of x, is 4.2. I would highly recommend you pause the video as we go through and try your state plan, do, and conclude all along, because I have a feeling you could definitely do this problem without me. But Let's start. We're going to start with A, just the part that's like construct and interpret the interval. We'll get to B eventually. So state, we would like to estimate the true mean time spent on homework for students at the school with 95% confidence. Remember, we're really just saying what we're finding. In our plan, we want to say what we are going to use, which inference method, and then check our conditions. Because we are estimating mu, the true mean time, and there is only one sample here, I am going to use a one sample t-interval for estimating population mean. Sorry, I just had to pause that. A student zoomed into my room unannounced. And where were we? We were on the plan. So we'll use our one sample t-interval for estimating population mean, assuming the following conditions are met. We have to make sure random, normal, independent. Obviously, the easiest one to check is random. We know it's random because they mention it in a random sample. We check normal by checking the central limit theorem, and luckily it holds here, so we don't really have to do much, and is greater than or equal to 30. And our independent condition, n is less than or equal to 1/10 of our population. 250 is less than or equal to 1/10 population. Solve that for population. There would be more than 2,500, what are we looking at? Kids. And if this is a large high school, that is very plausible for a large high school. Sorry about that. Oh my gosh, hold on. Now to the do. So our one sample one sample t interval is right here. X bar plus or minus t star times the standard deviation of our sample divided by the square root of n. Our degree of freedom is n minus 1 of 249 because I need my inverse t, my t critical value. Inverse t, the area, so if it's a 99% confidence interval, because that's, just kidding, 95%, then we have 2.5% right here, and 2.5% right here, which means the area to the left is 0.025. Our degree of freedom is 249, which would give me a t critical value of 1.97. My mean and standard deviation were given to me. I plug them all into my formula, and as promised, you don't have to type that all in. What we can do, and I wish I could show you my calculator, but I don't have the calculator app on here, but if you click Stat, scroll over to Tests. Right now, we are doing the one sample t interval, so it is the option that says t-int, which I believe is option 8, I think. It's around there. And when you get here, it's going to ask you two things. It will say, or it'll give you two options. It'll say input, and it'll say either data or statistics. Now, if we were doing the last problem, so the one on toilet paper, where they gave you just a list of the data, that would be what you want. In this case, we don't have a list of the data, we have the statistics. So we want to highlight statistics. Then it asks you for your X bar, which we know is 10.2. It asks you for your standard deviation, your S of X, 4.2. It asks you for your sample size, 250. And it asks you for a C level, which we are going to put as a decimal, so 0.95. Add that all in, let your calculator do all the heavy lifting, and hopefully you get the interval of 9.68 to 10.72. Once we have our interval, we have done our do step, and we need to then conclude. We are 95% confident that an interval from 9.68 to 10.72 captures the true mean hours spent on homework at this school. And then let's look at the last question. This is a good one. Based on our interval, what can we conclude about the principal's claim? So the principal's claim, it said a principal at a large school claims that students spend at least 10 hours per week. The principal says, my students spend at least 10 hours per week. So he's saying the true mean is greater than or equal to 10. Looking at our interval, what would you say? Do we agree with his claim? Or do we disagree with his claim? Pause the video and get an answer. But really, we're going to disagree with his claim. Our interval contains values that are less than 10. So it does not support his statement saying students have at least 10 hours, because it's possible that they only spend 9.6 hours or 9.7 hours or 9.8 hours. There are values in that interval that do not coincide with this. So we would say, hey, that principal is probably lying. That, my dear friends, is the end of chapter 8. So congratulations. Next time we have class, we'll do some review, and let me know if you have any questions.